In chip design, global placement determines the exact XY location for every logic cell on the chip. DREAMPlace, introduced in 2019 by researchers from UC San Diego and UT Austin, frames this step as an end-to-end differentiable optimization and harnesses GPUs alongside PyTorch and TensorFlow to achieve minute scale, Python-driven placement. This presentation shows how DREAMPlace reframes global placement as a GPU-accelerated differentiable optimization, discussing differential global placement, unified wire length and density loss, adaptive Lagrangian penalties, GPU-accelerated gradients, local repulsion via pseudopins, and AI framework prototyping. Global placement is formulated as an end-to-end differentiable optimization that enables backpropagation over cell coordinates. By recasting global placement as a fully differentiable optimization, DREAMPlace treats every cell's XY coordinate as a trainable parameter. Global placement becomes a single end-to-end differentiable loop, starting from a random layout, computing wire length and density gradients in parallel, applying a combined update, and repeating until convergence. The resulting coordinates then proceed to legalization and detailed placement. By treating nets as input samples and cell positions as network weights, the loss function depicted in the right panel serves as an error plus regulator with backpropagation, computing exact gradients for every XY parameter. Building on the end-to-end differentiable formulation of global placement, the next slide synthesizes these objectives into a unified loss function that drives simultaneous wire length reduction and density control. Merging wire length and density into a single differentiable loss enables end-to-end gradient descent. Here, the unified loss function, LW, combines total half perimeter wire length, HPWL, with a smooth density penalty, DW, scaled by lambda. Each gradient step simultaneously pulls closer along nets and pushes them out of crowded bins. The two heat maps illustrate how initial wire density hotspots are eliminated. And the loss curve confirms rapid and stable convergence under end-to-end gradient descent. This approach combines wire length minimization and overlap avoidance into a single differentiable loss function, enabling each gradient step to shorten connections and optimize cell spacing simultaneously. Notice in the plot the smooth monotonic decline and the converged marker around iteration 200. This demonstrates that end-to-end gradients drive rapid convergence. With a single differentiable loss now governing both wire length and density, the next step refines overlap control. So the next slide shows learnable Lagrange multipliers and adaptive penalties, replacing costly projection setups, ensuring smooth GPU-driven density management at scale. Learnable Lagrange multipliers replace costly projection steps, enabling smooth gradient-friendly density control at a 10 million cell scale. Discrete legalization on 10 million cell layouts is prohibitively expensive. DREAMPlace instead embeds overlap control directly into continuous loss, solvable with the same GPU-driven gradients that shrink wire length. A quadratic form ensures differentiability, and the self-adaptive lambda scheduler amplifies the penalty only when needed, preventing both under and overcorrection. The before and after maps then close the loop. Few to no hotspots, uniform defense density, and legal placement are achieved in minutes rather than hours. The next slide illustrates how offloading these gradient passes to GPUs yields sub-minute overall runtimes. Offloading wire lengths and density gradient computation to GPUs reduces 10 million cell runtimes from hours to minutes. CPU placers take about 3 hours for 10 million cell designs, which is too slow for modern agile workflows. DREAMPlace cuts that to 1 minute by running per net and per bin gradient kernels in parallel on thousands of NVIDIA CUDA cores. A fast SM-based reduction aggregates these gradients, then a single coordinate update pass applies them to all cells, and because each scales linearly, doubling design only doubles runtime. This GPU accelerated pipeline transforms placement from an hours-long wait to a minute scale process, enabling rapid design iterations. The next slide shows how pseudo pins add local repulsion to clear any remaining density hotspots. Injecting pseudo pins creates local repulsion forces, smoothing out residual density hotspots. Some bins still stay overcrowded after the global density penalty. DREAMPlace tackles these hotspots by injecting virtual pseudopins into each congested pin. Each pin emits a smooth, squared distance repulsive force that pushes nearby cells outwards. These local gradients merge with the global wire length and density gradients in the same linear GPU pass, so no separate legalization is needed. The before and after mini heat maps confirm the result. Stubborn red hotspots turn uniformly green within a few iterations. Next, the next slide illustrates how deep learning frameworks transform these algorithmic ideas into straightforward Python code. DREAMPlace leverages PyTorch and TensorFlow deep learning libraries to enable rapid development and experimentation of placement solvers. DREAMPlace distinguishes itself by treating placement like training a neural network, all in Python. In one line, the combined loss blends HPWL and density overflow. A single loss backward call invokes automated differentiation to compute gradients for every cell coordinate. And the optimizer step applies those updates in parallel on the CPU. Because PyTorch and TensorFlow handle CUDA kernel generation and TensorFlow ops, experimenting with new penalties, lambda schedules, or optimizers is as simple as editing a few lines of code. This AI framework integration turns placement solver development from months of C++ engineering into an interactive, high productivity Python workflow, fueling rapid innovation at chip scale. In conclusion, DREAMPlace fundamentally rethinks global chip cell placement by treating it as an end-to-end differentiable optimization. A single loss function combining HPWL and a smooth density penalty lets gradient descent shorten interconnects and eliminate overlap in tandem. Adaptive Lagrangian penalties automatically intensify only when bins threaten to overflow, while pseudo pins inject local repulsion to blast away stubborn hotspots. All of these gradient steps run on the GPU in linear time, placing 10 million cells under a minute, transforming placement from an hours-long slog into an interactive workflow. By building on PyTorch and TensorFlow, DREAMPlace replaces months of C++ engineering with a few lines of Python. Researchers can define new loss terms, tweak lambda schedules, or swap optimizers and immediately see the results on silicon scale designs. These AI-empowered innovations not only shatter scale limits, but also pave the way for next-generation flows. Timing-driven objectives, power-aware placements, and even co-optimization with routing. DREAMPlace is the first step towards a future where chip placement is as agile and as adaptable as training a deep neural network. Thank you.